Yeah, so today, join me in welcoming Ajay. Ajay is a sixth year PhD student advised by Professor Saman Amarasinghe, who is also here with us today. Welcome, Professor. At CSIL MIT. His research interests are making it easier for folks to create their own programming languages with a focus on high performance system domains. In the past, he has worked on DSLs for domains like graphs and networks, targeting a variety of architecture like GPUs, CPUs, and domain-specific hardware. His current work on Build It, which he'll be talking about it today, makes the process of designing and implementing DSLs easier, while also providing other toolchain support like debugging. Welcome, Ajay, and the floor is all yours. Thank you.
Hi, thanks a lot for introducing me, Ashutosh, and thanks a lot, folks, for having me here. This is a really fun opportunity. I grew up in India, and I spent a lot of time working on compilers in India, but I really miss not having such an like a close net of like group of people talking compilers and having socials. I was in India till 2018, so I think I barely missed LLVM socials uh, first iteration. But I'm glad, and I'm happy to sort of like talk about my research and hear about what folks are working on these days. So, okay, I'm just gonna share my slides and I'll get started. If you have any questions, just please hold on to them for a bit. I'll stop. I'll pause in the middle and ask for questions if there are any. I don't want you to wait till the very end, but if we wait for a while, that would be great. Okay. Uh, so I'm using Teams for the very first time, so I'm still figuring this out, but I think this should be good. Okay, you guys can see my screen, right?
Yes, yeah.
Okay, perfect. Good evening, folks. My name is Ajay. I'm a sixth-year PhD in the Commit group. We work on compilers. Surprise, surprise. Today's talk is going to be about democratizing high-performance DSL development with Build It. There's a keyword here, DSL. I'll explain that what that means, but a little bit of background into how I got here. So in 2018, I started my PhD. This is me in my first year, running around my scooter. And the day I came to the lab, I noticed that I'm just surrounded by DSLs. So what are these DSLs? DSLs basically stand for domain-specific languages. So these are programming languages, full-fledged programming languages that you can use to write applications, but they are slightly different from your typical programming languages like C++ or Python or Java or Rust or whatever you use today, in that they are made specifically for a problem domain. So they are not general in the sense that you cannot write any kind of application with it. They are well suited for writing applications for a specific domain. So here I have some 4 examples of all the DSLs that came out of our group. Halide is probably the most popular one, and you might have heard about it before. Halide is a DSL for targeting applications from the image processing domain. So if you want to write some in fact, this is being used in Adobe right now in Photoshop to write filters or write a lot of the image processing pipelines. The other DSLs that we have currently in our group is Taco, Graphit, and Tiramisu. Taco is basically a tensor algebra compiler, so all sorts of computations like matrix multiplication, sparse or dense, matrix vector multiplication, or even complex expression involving multiple operations. You can write programs for that, compile them down into really efficient code, and execute it. Graphit similarly is another DSL focusing specifically on graph applications. When I say graph applications, I mean things like shortest path or BFS, small like applications like that, or even complex chains of such applications can be written with Graphit. And finally, Tiramisu is a polyhedral compiler. So it focuses specifically on kind of loopness that fit well into the polyhedral model. So yeah, when I came to MIT in 2018, I was surrounded by these DSLs, and obviously it was very fascinating because I had not worked on DSLs before. I actually started contributing to the Graphit DSL specifically. I was working on the GPU backend at the time. So let's actually just take a look at how Graphit works as a DSL. So Graphit actually takes 2 inputs. The first is what we call the algorithm input that I've shown on the left-hand side, which basically describes what you want to compute. So what's your computation? What is the result you're trying to compute? Here it's showing an example of a function that's applied to every edge. I think this is from I think this is on PageRank. So what this is basically doing is summing up the weights, the contributions from the neighboring edges, and updating the ranks of each vertex. But on the right hand side, what I've shown here is what we call the scheduling input. What that means is it's an input to the compiler, to the Graphite compiler, to tell it how to compile this code. Because this same code can actually be compiled in different ways, and it will have very different performance characteristics. So the scheduling input basically tells the compiler, hey, this is how I want you to compile it. And then the compiler takes this code and generates different sort of outputs for CPUs, for GPUs, and for even modern hardware like ASICs or some specialized architectures. These were our past work where we generated code for different architectures. This is Graphite story. You have algorithm, you have schedule, you generate code. But actually, if you look at other DSLs in the group, like suppose you look at Taco, Taco has a similar model where you have an algorithm specification where you specify what you want to compute. Here, it's an example of a matrix vector product. And then you separately have a scheduling language which tells you, OK, I want you to split this loop with these indices. I want you to reorder these loops. I want to parallelize these loops. So all sort of like optimizations that we have seen before in traditional compilers, you apply to those inputs, and then it generates sort of low-level C code for you that you can run on your CPUs or GPUs. I think Taco now currently supports CPUs and GPUs. So a very similar story to Graphite in that sense. And if you actually look at the other DSLs, Halide also has a similar story. So the question I asked myself looking at this 5-6 years ago was, why do we need n different compilers to do n different languages? And when I say n different compilers, these are not small compilers. If you look at the lines of code of some of these, like Tiramisu, it's 350,000 lines of code. That's not as big as LLVM, but it's certainly bigger than many of the other compilers that you see out in the wild. The smallest one, Taco, is also 71,000 lines of code. This is including all the runtime and the compiler implementation, but that's still a lot of code that's been written for each new domain. So the obvious question I asked myself was, how can we reduce this effort? Taking a step back, let's look at this problem in a sort of abstract way. Let's forget about Taco, Halide, Graphite for now. Let's just look at a foo DSL compiler that takes this approach. So I have a foo DSL compiler in the middle. On the left, I have the algorithm input, and then I have the schedule input. So what makes these compilers different? What makes a compiler 1 different from compiler 2? Inside the compiler, there is baked in domain knowledge. So each compiler knows and understands its domain and uses that knowledge to optimize the code. For example, when you have Graphite, which is a graph DSL compiler, it basically knows what does it mean to be a vertex set, or what does it mean to have a set of edges, and what does it mean to apply a function to a set of vertices. And how can I optimize it? That's the domain knowledge that comes specifically from that field. It cannot be like transferred to other compilers. And that's what makes each of these compilers unique. I can give you more examples from other domains, but the idea is there is some hidden knowledge inside the compiler that the developer has baked into the compiler, which makes that compiler special. So my obvious first thought was, what if I take this domain knowledge and make it into a third input to the compiler? So we'll still have the algorithm, we'll still have the schedule, but we'll also make the domain knowledge encoded as an input. And then what I will have remaining in the compiler will be a generic DSL compiler. So I do not need a separate compiler now. I can just feed in the domain knowledge as an input and reduce that sort of overhead or that work that we had to put into develop multiple compilers. And I started out with this idea. So I started like going and talking to the folks who have worked on these DSLs, the senior PhDs in my group who were working on these projects, and I asked them, what's the process of making these DSLs? So what I eventually, after talking to like a lot of people, what I realized is making these DSLs is usually a three-step process. The first step is creating abstractions. What this means is you have to understand your domain first. Like if you're writing a DSL for image processing, you have to understand what are the types of data that you're going to deal with. Is it going to be images? Is it going to be arrays? Is it going to be sets of data elements? Or what are the type of data you're going to deal with? And the second part of the abstraction is understanding what operations you're going to do with them. So just going back to the graph example again, one of the types that we have there is a set of vertices. And one of the operations we have there is take this function and apply it to every vertex in this set. That's the kind of abstraction that you have to first understand. The second step in writing these compilers or creating these languages is figure out optimizations that make sense for that domain. These optimizations, when I say optimizations, I don't mean optimizations like lower level optimizations like register allocation or parallelization maybe fits into there, but not things like instruction selection or things like that. What I mean here is higher level optimizations. So when I say an operator like apply this function, the key decision you have to make at a higher level is, do I want to apply these in parallel? Do I want to apply this function? Can I reorder the way this is applied? Can I split this optimization? Can I split this operator into two parts? Can I merge two different operators into a single loop or so on? So these are like higher level domain specific optimizations that you need to figure out. That's the second step. And the third step finally is to generate code, like write a compiler, parse your input, do some transformations, do some analysis, use that schedule that the user specified, and finally generate low-level code. So these three steps sort of like are common across all the DSLs that I observed. I also noticed that these DSLs, these folks, the creators of these projects actually worked with the domain experts to come up with these compilers. And actually, the first two steps, the domain experts are very familiar with. And what I mean by domain experts is people from these domains who are not compiler engineers or compiler researchers, but actually use these domains. So for the image processing DSL, they worked with some of the professors from the image processing field at MIT, and they gave inputs on how to create these optimizations or how to create these abstractions, because these folks have been writing libraries, high performance libraries for these domains for a long time. Just go out and look at any of sort of like high performance libraries, and you can see that these libraries have like similar abstractions, operators, optimizations baked into them. What these folks do not know is how to write a compiler. How do you take these optimizations to the transformations, to the analysis, and generate code? And that's the sort of like gap I wanted to fill in. But before I go into how we did it, I just want to give again some examples of what really is this domain knowledge that I've been talking about. Like, what's a concrete example of what this domain knowledge is? So just like I talked about before, Graphit, this is an input from the Graphit programming language. It has, I've shown here some types and some operations. So the two types I've shown here is edge set and vertex sets. As the name implies, edge set just holds a bunch of edges in a set to do some operation on, and vertex set just holds a set of vertices. Now the operations on these are a little bit complex. So for example, here I have edges.from active set dot not visited dot apply update edge. The way you read this is take the set of edges and apply the function update edge on it. That's the basic operation. But there are a few extra clauses. So what it says here is filter out those edges that originate from the active set. What that means is take those edges whose sources are part of the set of vertices active set. Right? A vertex active set is a set of vertices as defined above. So you filter out the edges that originate out of a particular set of vertices, and then the .to is basically a filter function. So what it's saying is for every destination of the edge, run this function not visited. If it returns true, keep it. If it doesn't return true, discard it. So it's basically filtering out edges based on source and destination, one using a set, the other using a function, and then applying the function update edge on the filtered out edges. This is like sort of an example of types and operations that we have in the Graphit domain. Okay, so how would you compile this down? What are the different ways you can actually implement this? The first is an example of what code you would write if the active set was sparse. What I mean by sparse is if the total number of vertices in the active set are much smaller than the total number of vertices in the whole graph. If that was the case, the way you would implement this is you would have a loop for v in active set.vertices. So you would have a loop that goes over all the vertices that are in the active set because you're filtering based on that. Then you would have another loop that goes to the neighbors of those active sets. So instead of starting with the all the edges and then filtering them out based on the source vertex. You just start from the vertices that are in the active set, iterate through its neighbors, then check the destination property. So check if not visited returns true. And if that returns true on the neighbor, then you call the update edge function on v comma neighbor. This is like the simplest example of how you would implement this function if the active set was sparse. But however, if the active set was dense, what I mean by dense is a lot of vertices are active, which means that iterating through them through a set like this would be very expensive. So the way you would do that in this case is, first of all, you would convert the active set into a representation that's dense. So you would convert it into like a bitmap or a bool map or just an array of ones and zeros that would tell you whether that that vertex is in the set or it's not in the set. And then the way you would implement this is you would iterate through all the source and destination pairs in edges, the active set. Then you would check if the source is in the active set. And this can be done quickly now because we have stored the active set as a bitmap. So you can just do a single lookup to check if the source is active or not. And then you would check the destination property and finally call the function. Similar implementation, but slightly different. And then finally, if the active set is too large, like if the active set has almost all the vertices active, you actually can further optimize this. The way you would do this is, instead of iterating through the edges in a forward way, which we call the push direction, so like pushing values from the source to the destination, you would do what is called a pull iteration, where you first transpose the graph, iterate through all the vertices that are passing the destination filter, and then taking all their neighbors and iterating through checking the property if they're in the active set, and then calling the update edge. There's the reason why this is more efficient. It's because when you can basically eliminate a lot of vertices based on their destination, a lot of edges based on their destination, and you never have to go through the loop of actually iterating through their neighbors. That ends up like actually saving a lot of iterations through a bunch of edges. But anyway, these are high-level optimizations that make sense for just this one line of an operation. Now, how would a traditional library writer handle this? Like if you were a library writer and you wanted to write a library for this domain, how would you implement this operator? Typically what they would do is basically wrap this code into a bunch of if conditions, which specifically check what properties are described. So if active set is sparse, do this. If active set is dense and if it is not very large, do this. If it is large and dense, then do the final operation. This is the natural way how the library writers would handle this. But there's a problem with this. Okay, first of all, the domain experts know how to do this. They do this all the time. But the problem with this is that these checks, these conditions would be checked at runtime, and that has a cost. Now, for this specific example, the cost is not very obvious because the checks are sort of at the outermost level. The work is inside the check, so the check happens once, and you can be done with the check. But actually, sometimes these checks also appear in the middle of the loop. So the update edge function, depending on how it is implemented, also has similar checks inside it. Now, imagine having to check that condition every single time the loop is invoked. And the hardware really can't help you here either, like through branch prediction or through like instruction pipelining, because these conditions are really not fixed. Like sometimes they could be true, sometimes they could be false, depending on which edge you're processing. So the point is, without doing explicit code generation, the performance here is going to be really bad. So, and we have seen that, especially when you're running an architecture like GPU, which cannot tolerate any sort of like diversions or any memory bottlenecks, this becomes a problem. So how do we sort of help these DSL or these library writers make DSLs out of it? That's where my thesis or my project Build It comes in. Build It basically is a library that lets you write compilers. It basically takes your library code that you have written and automatically makes it into a compiler. And I'll get into how that works and explain how we make DSLs with it. But before I go ahead, I want to take a minute for taking questions because I've covered a lot of DSL stuff. If there are any questions at this point, I'm happy to answer, and then we can move on. I'm also gonna try to see if I can look at the chat. Actually, can't see the chat. If there are any questions in the chat, please just someone read them out to me.
There are no questions in the chat, but so maybe so does the schedule or how do you find the optimal code generation in your pipeline, right? So you've described an algorithm and you have a schedule, and do you encode that information in the domain knowledge part, or is it part of the schedule?
That's right. So some part of the optimization is baked as part of the domain knowledge because for some operations, there's an obvious choice. Like, this is the most efficient way to do it no matter what. Where the scheduling language comes in is when that decision is dependent on the data. So for example, if you have a graph, so graphs are different from each other, right? Like you have some graphs that represent, say, roads around the world. Like if you have a map of edges showing the roads between different cities, say in India, that would be a different kind of a graph from a graph that shows, say, the Twitter following, like who follows who kind of a graph. That has very different characteristics, which means an example of that would be the road graph would have a very bounded degree, which means like each city has up to like 8 to 10 neighbors. But a social graph would basically have thousands and 10,000s of neighbors for some vertices, while some vertices would be very small. Now, very different optimizations make sense for these two graphs, and that's what we encode through the scheduling language. So the scheduling language basically tells the compiler, okay, I have some understanding of what the data is going to be, and that's why this optimization makes sense. Now, someone has to make this decision. In most cases, we expect the user to write this input. The scheduling language is sort of like we try to constrain it as much so that they don't have to like specify too much input. But then you can also use like auto-tuning techniques to automatically come up with the schedule. So you can, like, if you can provide the data that you're going to run it on, like sample data you can run it on, we have systems that can sort of like try to iterate through different schedules and figure out what the best one is, and then sort of generate code for it. So the first step is to sort of have a scheduling language that the user can use, but then you can extend it to sort of become automatic based on data.
Okay, yeah, thank you.
Yeah. I mean, okay, if there's questions about this later, we can take it again, but I'll continue for now. So, okay, introducing Build-it, a tool that automatically converts your library code into compilers. Before I talk too much about Build-it, let's just see what it is. Build-it is basically a type-based multi-stage programming library in C++. The C++ part shouldn't alarm any of you guys here because all of you are LLVM developers. I'm assuming you understand, that C++ is kind of like the language of choice when you're writing high performance code, or if you're generating high performance code. We specifically decided to take a library approach as opposed to a compiler approach so that these library writers can quickly adopt this and start using it. Like, we do not want our system to look like a compiler. We do not want them to understand how to write transformations or analysis. So Build-it is basically a pure library you can include inside in your code with like hash include or pound include Build-it, and you can just link with it and run it. So, but the key part here is it's a type-based multi-stage programming framework. What does multi-stage mean in this context? So here's a typical workflow of how you write a program. You have some input, you pass it to the compiler, you get an executable, then you feed in the input and you get an output. This is our typical C++ workflow. We all know this. What multi-stage programming does is it takes it a little bit forward. What we have is you feed in the input, compile it, get an executable, provide some of the inputs, and the output that comes out of it is again more code. Then you pass that code again through C++ compiler or whatever compiler that you're using. It gives you an executable again, where you provide rest of the inputs, and then you finally get an output. This is sort of like a multi-stage compilation and execution pipeline. We can actually repeat this as many times as we want, but for the sake of like simplicity, I'm only going to talk about like 2 stages today. So this is what Build-it gives you. It lets you write it gives you the ability to write code in stages. And the 2 inputs that I have here, they are not the same inputs. They are different, basically parts of the inputs that have been separated over time. Let's actually take an example and see how it works. So the way Builder sort of like specifies what the inputs, what stage the execution happens in is through types. So in the system, we introduced two new type templates, dynvar and static var of t. These can basically be wrapped around most of your C++ types. Dynvar represents values and expressions that are that will be generated as it is in the code. While static var represents types and variables and expressions that are completely evaluated in the first stage. So for example, here I have a power function that takes two inputs, base and exponent, and computes basically base power exponent. It does that through repeated squaring in this case, so it's an efficient algorithm. And what I've done here is I have annotated, or I've declared base to be dynamic var of int. What that means is this input will be specified in the second stage as opposed to in the first stage. And I've specified exponent to be a static var, which means I will provide that in the first stage execution. And it returns a dynamic var because the output is dependent on both of them. And if you look at the implementation of this function, it looks exactly like you would write normal a C++ function to implement base power exponent in a single stage. And then when you execute this with the inputs, so in this case, I'm specifying exponent to be 15 in the line below where I say extract function power 15, 15. That 15 is the input for the exponent. This doesn't have to be a constant. This can also be a runtime input coming from the user, reading from a file, whatever, wherever that value can come from, that can be an input. And so what this generates now for us is this specialized function power 15, which takes a single argument, which is the base, and computes that base power 15. So what has essentially happened here is Builder has specialized this code power function for the input exponent equals to 15. It's basically partial evaluation of this function. And the benefit we got out of this is all the control flow, like the exponent is greater than 1, the while loop, the if condition, which only depends on the static input, is completely evaluated. So we basically get this unrolled code without any branches, without any loops, which should run faster in principle than the function on the left if it's happening in a tight loop. But what about the case where I suppose want to do the other way? Suppose I want to keep the base as the first stage input and make the exponent as a second stage input. So I want to specialize the implementation for a specific base. In that case, I just have to change the type. So between the two versions, the code looks exactly the same. All I have changed is the type of the arguments. So in this case, I've specified the base to be static variable and exponent to be dynamic variable. And the rest of the code remains exactly the same. And in this case, what Builder generates for us is basically this power 15 function that still takes one argument, which is the exponent in this case, and computes 15 power that exponent. Now, because the control flow here, the exponent modulo 2 is all dependent on the dynamic variable, that has to be pushed to the second generation, second stage. So in the generated code, we basically have a while loop, we have if conditions, we have all the operations that happen on the dynamic finally returns a value. So the basic idea I'm trying to get at here is Builder can basically generate code based on, like, just by changing the types, you can change what code is generated. And the benefit of this approach is it has full C++ language support in all stages. So this is not like a constrained language like C++ templates where you have to sort of like rewrite your algorithm to do computations in sort of like the compilation stage by writing it as templates or const exprs or all the sort of like restrictions that come with it. In both the stages, you have full C++ support. So you can implement hash maps, you can have stuff being read from a file, you can run complex algorithms, you can basically do anything you can do in a C++ language in all the stages. And it generates code by partially evaluating stuff that's declared as static. Okay, so that's the basic idea of how Builder works. So how does it actually do this? Like this on paper sounds like a nice thing, but how do we actually implement a library that can do this? So if you're ever trying to sort of like embed any of these systems in a language like C++, the usual starting point.
Sorry to interrupt. I think there's a question.
Sure. Let's take the question and then I'll continue with this. Yeah.
Thanks. Thanks. This is Saurav Bansal from IIT Delhi. So I just wanted to understand this. So I understood the example that you gave, but I mean, isn't this also possible through template programming, meta programming? And I guess you said something about full C++ support not being available there. So perhaps I didn't understand it fully.
Yeah. I'm happy to clarify. So what I mean is, yes, you can do exactly all of this through C++ templates, and it will probably give you the same performance as what we get here. But the key idea is, if you look at the code for the 2 stages that we have, it is exactly the same. So the condition in this case on a first stage variable just looks like a normal if condition. The if condition on a variable that's going to be evaluated in the second stage also is a normal if condition. With templates, you would have to write it as a combination of either const expr expressions, or you would have to write it as a template matching, which is significantly different from like the normal C++ that you write. And the problem there is, now if you need to change sort of what stage a particular expression evaluates in, you have to go and rewrite the whole code. In our case, you just have to change the types. You just change this declared type to be static or dynamic, and it will control basically what stage it evaluates in. That's sort of like the technical reason why this sort of approach is easier to use. But in general, also, when you go and talk to these DSL folks, they do not want to write templates. Like templates for writing sort of the templates do multiple things, right? Meta programming through templates is something that is significantly harder to do than just use templates for like generics. And we want them to be able to quickly sort of like take their existing code bases and migrate it to this system without having to rewrite it. But if they want to do that through like templates or const experts, they would have to rewrite a lot of that code base. And that's what we're trying to like simplify here. I hope that makes sense.
Yes. Okay. Thank you.
I guess I'll go through some more examples, and maybe it'll be clear how this approach is different from templates or previous approaches. I mean, you can also do this through like compile.
I have one doubt actually. So
Yeah,
how would an end user know which variable to declare as static var or din var, and which is going to give him an optimal code if he doesn't have any compiler based or compiler optimization based knowledge?
That's right. So that actually is a very it's that question actually goes beyond just writing DSLs. That's a very general question about metaprogramming. Like, how do you decide which variables and which part of the input should be evaluated in the first stage and the second stage and the third stage? The general rule of thumb that I like to prescribe is if you have a set of inputs, the inputs that are changing very often should be in the following stage. The ones that's not changing as often, you want to specialize for that. Because here's the thing, there's a cost to generating code. Like when you specialize code for something, you have to invoke the compiler, you have to compile that code, and then you actually can run the generated code. So you want to avoid recompiling as much as possible. Like you don't want to compile for every single change in the input, right? You want to sort of amortize the cost of that compilation as much as possible. So you want to specialize it for the input that's not changing a lot. So in this sort of the Steinvar, the power example, if you specialize it for an exponent, and you know that I'm going to sort of like compute power 15 a lot for different base values, then it makes sense to sort of compile this version. But if your exponent keeps changing as much as your base, there's no point in specializing this. Then you're basically going to invoke the compiler so many times that you'll actually kill your performance in that case. So it's just a matter of like which inputs change a lot. Going back to the DSL example, the schedule often doesn't change a lot, right? Like when you know that you're working on a specific domain, your graph type, suppose, is not going to change a lot. Like you're not suddenly going to start running the same algorithm on road graphs when you're previously running it on a Twitter graph. So those kind of inputs you would specify in the first stage, but the kind of like the actual data you're computing on, like the actual graph, would be pushed to the second stage. That's sort of like the rule of thumb. Again, that could change for certain cases. Like sometimes it makes sense to specialize for something, even if it's not changing too much. Even if it's changing a lot, just because of I don't know, like the evaluation cost might be less depending on which hardware you're running on. Like you could compile on a different hardware, you could run on a different hardware, and if the hardware you're running on is very constrained, it might still make sense to specialize it beforehand. So that could depend. But yeah, generally, if input changes a lot, push it to the second stage. If it doesn't change a lot, evaluate it in the first stage. Okay, so yeah, let's go ahead with this. And if there's any more questions, I'm happy to take them. Okay, so how does Bullet work? How does it do this sort of two-stage executions in C++? We start with a simple idea of just overloading all the operations, and I'll show what I mean by that. So we have this type denvar of t, which is basically the variables that we want to push the execution to the second stage. What that means is we do not want to evaluate these variables. We want to generate code for them to be evaluated in the second stage. So what we do is we overload all the operators that we have on this dynamic var t and instruct it to generate code instead of evaluating it. So for example, whenever the language or the library sees code like this, there's a declaration of two variables declared dynamic var. It basically produces the code for that in the second stage. So the constructor of denvar here is overloaded to print out basically a declaration of the same type. If there's an initialization, it produces code like int var1 equals to 0. This is trivial to do. Like you just change the constructor to print out code instead of actually initializing anything inside it. When you have an operation like x plus y multiplied by 2, the star and the plus operations are overloaded here. So in this case, it again produces code var0 plus var1 into 2. Again, it's just printing out the code as part of the operator overloading. The key point to notice here is that no actual computation is happening. So whenever plus and star is overloaded, x and y actually do not have any concrete values. They're just placeholders. They do not actually hold an integer inside them. They're just saying, okay, I'm a variable called var0, I'm a variable called var1, and I'm going to do an operation plus and star on them. Basically sort of like symbolically evaluating them in some way. And then you continue with this. If you have assignments, C++ thankfully allows you to overload assignments, so you can do x equals to x plus 1 becomes var0 equals to var0 plus 1 in the generated code. You can even, in fact, in C++, you can even overload function calls. You can overload array indices, address of operations, and a lot of things. And that makes it very, very easy to generate code like this. So this foo bar here, foo underscore bar here, is declared as a dynamic function. So it's a dynamic of type function. So all the operators are overloaded on it again, including the function call operator. So whenever you say foo bar of z0, it actually produces foo bar of var30. I'm not sure the declaration of var3 here, but z is basically var3 in this case. The ampersand operator is also overloaded to produce ampersand instead of actually taking the address of the variable. And this is straightforward. This makes sense, right? Like you want to generate some code for some operation, you just overload all the operators. But what happens when you have something like this? Like if I have an if condition based on a dynamic variable, like a variable that does not have a concrete value. Like if I write x equals to 3, I do not know if x is 3 or if it's not 3, because like I said before, these variables don't have concrete values. So how do you actually generate code for this? And that's one of the first challenges that we tackled through this in this system. So it's basically sort of like a workaround to not being able to overload operators, basically control flow operators. What you can overload in C++ for all types is implicit conversion to bool operator. What this means is whenever the user tries to, explicit conversion to bool operator. What this means is whenever you try to convert a variable of type dynamic var t to a bool value, like a first stage bool value, it calls this explicit cast to bool operator. The C++ insert this. This gets inserted whenever you have a condition on a variable. So when you have if x, and if x is of type dynamic variable, C++ will try to call this operator to actually convert it into bool before evaluating the condition. And that's where sort of we insert our magic to extract the condition. So here's how we do it. Let's look at an example that has a few dynamic variables. So we have dynamic x equals to 0, we have dynamic y equals to 1, and then a bunch of conditions based on x, y, updates to y, and finally a final statement. So, okay, let's repeat the process that we saw before. X equals to 0 produces x equals to 0, y equals to 1 produces y equals to 1. Now the execution reaches this x equals 0 first. That produces x equals 0 as it is. We haven't reached the condition yet. And at this point, the implicit cast to bool operator is explicit cast to bool operator is called. What we do is whenever this happens, we sort of remember what it was called on. So you put a marker on that statement x equals 0, saying this expression x equals 0 was converted into a bool. And then what we do is we basically explore the paths. So we say, okay, let's see what happens if this x equals 0 was true. And the way we do that is from this operator, we return true. And because it's bool now, it's not dynamic variable of bool, it has a concrete value. So we return a concrete value true to see, let's see how the program progresses if x was indeed 0. Because we return true, the evaluation goes to the then branch of the if condition, and we get the statement y equals to 2, proceeding as before. And finally, the execution reaches this last statement, and we get z equals to y. This is how we got sort of like a trace of a program, assuming x equals 0. But what if x was not 0? How do we explore that branch? So what we do is we start the execution again. We remember that, okay, we have explored some part of the program. We haven't explored all of it. So we restart the execution. Again, we get x equals to 0, y equals to 1. We get x equals 0 again, because that happens before the if condition. And now when we reach here, we see, okay, I have a marker on this x equals 0, which means I've explored the true path. So this time I'm going to explore the false path. So this time from the bool operator, we return false. And naturally, the execution goes the other way. So we get y equals to 3 as a statement. And finally, we get z equals to y. So at this point, we have sort of concluded our execution completely. We have basically these two different traces of the program under different conditions. And then, but this is not an entire program, right? Like we still need to get one program out of it. So then what build it does is it sort of like walks through the program and tries to merge it as much as it can. So obviously the first part, x equals to 0, y equals to 1, and x equals 0 can be merged because they're exactly the same. The program leading up to the condition is the same. In fact, at that point, you can actually make it into a condition. So it says, okay, because the rest of the program depends on whether x equals to 0 or x equals not equals to 0, I'm going to put a condition there and keep the remaining two programs that I had seen as the branches of this if condition. And if you actually further look at the program, you can see that the z equals to y is independent of the condition. So you can merge that into a single statement. And this gives us our complete program. So without actually overloading the if condition in any way, we extracted the if condition out of our code. And that's the sort of the first step. Then we have code generation passes. We actually go and generate the C code or the C++ code for you based on what you're choosing. So this is how conditions work. And the basic idea is we explore all the parts to get the whole picture of what's happening in the program. There's a bunch of optimizations on this. Basically what the process I described can blow up very quickly. Like if you have 10 statements, 10 if conditions, one after the other, it's going to take 2 power 10 number of iterations to actually extract the program. We don't want that to happen. It blows up very quickly. So we have a bunch of like optimizations, memorization optimizations in the system itself, which actually doesn't explore all the paths. It only explores polynomial number of, I think like it explores linear number of paths based on the number of conditions, and the overall complexity comes to like n cube to extract the whole program, and n is the number of branches in the program coming one after the other. If your branches are nested, that's gonna be exponential anyway, because you have to sort of like generate exponential amount of code. Like if you have 10 if conditions inside each other, your program is going to be exponential in number of nested conditions. But I'm talking about here number of statements one after the other. So if you have like n statements one after the other, the bound comes to like n cube of the number of statements. So that's great. We can now extract if conditions and produce a code. But what about loops? Loops are again a similar control flow that you cannot overload. So here I have a simple loop, a while loop, the most generic loop that we can ever see. And how do I?
Sorry to interrupt. Yeah, so if you can go to the previous example where you have
Yeah.
the if condition. So, and you also mentioned that you have like many if else statements, and you said it's exponential. Do you also take the dynamic variable as a static array? So let's say a den var of int of 10, and you have x, and you have x of 0 equal to some value. Do you also analyze those statements as well, or it's just restricted to like built-in types?
That's right. So if you have x as an array type and you do x of 0 equals 0, or x of n, like suppose the index is also dynamic, like x of I equals 0, that whole thing converts into like an expression that also has like operators overloaded on it. So In this specific case, actually, when you say x equals 0, it's not actually the condition on x. It's the overload is on x equals 0. So the equals operator is overloaded to return like a special type, and that special type has the operator overloaded on it. So the expression can be as complex as you can imagine. Like you can have a function call in there, you can have an array index, you can have any sorts of basic operations, even like member access or whatever you have. And the if condition doesn't really care about what's there inside, because all it cares is, does this whole expression evaluate to true, or does this whole expression evaluate to false? That's the idea there. Yeah, so you could have any sort of complex expression there.
So let's say you have a function call inside the if condition. Do you also do some sort of interprocedural analysis where you also take the function call and then do an analysis on that?
Right. So that depends on what type of function call you have. Like if you have a normal function call that basically just like is another function that accepts dynamic variables and returns values, then the execution will first go there. Like the execution will go to that function, evaluate the body of the function, and the branch will then be on the return value, right? Like suppose you have if foo, where foo is another function in your library, and foo returns a dynamic variable. The natural execution will be you have to evaluate foo before you can evaluate the if. So we will first go to the body of foo, evaluate the results as statements, and then the return value will be inside the if condition. So that's the first case. But if your foo is also a dynamic variable, where it's just like an opaque value, I don't know what function I'm calling, then it will just insert a function call in a generated code. So it says, okay, I see a dynamic variable and a call expression on that. So I'm just going to put a call expression and the if condition around it. So yeah, it can handle both the cases. You can analyze through the function if the function is available. If it's an opaque function, it produces a function call.
Okay, yeah, thank you.
Okay, so let's continue with the while loop case. What happens when you have another control flow that's a while loop? So we actually start the execution the same way as before, where we start basically generating a code based on the statements that we see. The only key difference here is we have this notion of something called a static tag, which is basically an identifier for every sort of statement that we compile or that we evaluate. Like it's an identifier for each statement that you see in the program. We basically annotate the generated code with these statements. So I'm not showing what the actual static tags here are. I'm just going to show 1, 2, 3, 4 to say different tags look different. But in principle, these tags are a combination of the state of the static variables and the where you are in the program. So like where your current instruction pointer is and the whole stack is, we use that to create the static tag, which uniquely identifies each statement that we generate. So okay, let's start execution from the beginning. We say x equals to 0 gets the tag 1. Then we evaluate x is less than 42. That gets the tag 2. It's a different statement. And that's where the if condition is. So then we get x plus plus because first we return true just to explore all the paths. And then finally get x less than 42. So because it returned true, the execution went back to x less than 42 after evaluating the body. At this point, Piltet sees, okay, I'm getting this x less than 42. It has the same static tag as x less than 42 I have seen before. Like not only this expression is the same, it actually is literally the same expression, is the same statement because it's in the same part of the program and the static variables are all in the same state. So what Billet concludes is I don't actually need to explore this further. No matter how many times I explore this, I'm going to get the same trace of program. I'm going to get x plus plus, execution is going to go back to x less than 42. So instead of like keeping on exploring, what it basically does is puts a back edge there. So it says, okay, in the generated code, I'm just going to put an edge that goes back to x less than 42 because it's functionally equivalent, right? Like instead of going back and evaluating the same thing again and again, I'm just going to put a back edge. Great. This gives us the true part of when x is less than 42. What happens when x is not less than 42? We get the rest of the program, which is z equals to x. Just going back to the program, we had a z equals to x after the loop. So if we had returned false from where x is less than 42, we would get the statement z equals to x. And that produces an if condition just like we had seen before. But one of the sides of the if condition actually has a back edge that goes back to the if condition. Now, what basically Builder then has is a bunch of post-processing passes where it looks at this kind of control structure where it says, okay, if there's conditions and there's back edges, I'm going to try to convert it into a loop. So in this case, it basically converts that back edge and the if part into a while loop on that condition x less than 42. And the generated code then gets basically the loop that we had seen before. There's more passes here involved where basically if it sees some sort of an initialization on a variable, some condition on a variable, some update on a variable, it tries to massage it into a for loop just so that we get nicer looking code. But all that is functionally equivalent. All those passes that come later just try to modify the code to make it look cleaner, but keep the functionality the same. So I guess one of the takeaways here is you might not see the exact same code as you write, but it'll be functionally equivalent. Like you might write a for loop, you might get a while loop, but that's okay. It'll behave in the correct way. So yeah, with a small change of just adding these static tags, we are able to now extract loops. And that actually covers all of it. Like that covers, we have basic expressions and statements, we have function calls, we have if conditions, and we have all sorts of loop covered by it. And that's all you need for sort of like implementing dynamic variables and static variables. Static variables are, by the way, implemented as a very simple wrapper around T. So static of T is essentially just T. And because we wanted to evaluate in the first stage. So you can basically use static T as normal variables. Okay, so what does this, okay, so if this part is clear, let's go back to our DSL example and see what happens if we apply this technique to this code that the library writer had written. So we start from the same code that they wrote, where they have a bunch of conditions on the state of the type of the active set, like whether it's sparse, whether it's dense, whether it's small, whether it's large. And they had sort of different executions based on it. So the first thing that we'll do is all these sort of meta information about the sets, whether it's small, large, etc. We're going to make it as static. And we're going to keep the actual data that the vertex set hold and the edge set hold as dynamic. So all I've done here is between the two examples, just change the type of the variable. So the for loop in the int in the for loop becomes dynamic int. The active set dot is sparse becomes static. The active set dot actual vertices is a dynamic in this case because the vertices will only be known at runtime. And then that's all I've changed in this code. So I just change some types. And now what happens is when I specify in the first stage as the scheduling input, what does the active set look like? What does the edge set look like? These meta properties about the sets now actually based on those inputs, Build-It will just generate one of the branches. Like instead of generating the code on these, the if conditions will be evaluated in the first stage, and we'll get different code based on which input we had specified. So this is like our basic idea of how we are implementing a compiler. We basically have interleaved code of static and dynamic, and as you specify the static inputs, it generates different code. So these conditions again do not have to be at the highest level. Like you don't have to have an outer condition and just dynamic inside. You can also have like dynamic inside the a check inside the update edge function, and it would inline that update edge differently to produce different code. Like I haven't shown what the update edge function does in this case, but whatever the body of the update edge function is would be sort of inlined inside that if condition, because Build-It sort of like evaluates through it. And if there's any conditions there, it'll evaluate those, it'll produce different code based on those conditions. So by sort of like interleaving these conditions between your library implementation, you can get different sort of generated code that's like tailored for that input. So this is our like basic, very high level idea of how we implement DSLs with our system. But the obvious question to ask here is DSL compilers or compilers in general are more than code generators. They're not just generating code. You also have to analyze the code. You have to transform the code. You have to do some sort of, mostly analysis and transformations to generate the code. Sometimes you also have to generate code for different architectures, but that's a different thing. So how do we do that? And okay, remember, the constraint here is we do not want these library writers to have to understand how compilers work. We want this to happen in a more like library way as possible. So what we do is we actually use our static and dynamic variables to also implement analysis. So analyses and transformations, basically. Let me show an example quickly without having to go into too much detail. Okay, so here's the example of the update edge function that we had seen before, which basically takes a set of edges and applies this function update edge on it. For each of the edge, we are basically doing this new rank of destination plus equals to old rank of source. This line is this 3 lines of code is copied from the PageRank DSL implementation. So what is it doing here? It's summing up the ranks of the destination based on the sources. So what happens if this function is invoked in parallel, right? The new ranks of destinations could be written to by different threads at the same time based on whether that destination is mapped to multiple threads or to the same threads. And in that case, you might get correctness issues, right? Like you might need to insert atomics to actually make it run correctly. Otherwise, you will get race conditions. But you don't want to insert atomics all the time, right? Because if you insert atomics all the time and destination is actually only mapped to a single thread, then you're unnecessarily doing extra computation and wasting cycles, which is again bad for performance. So the easiest way to sort of solve this problem is to analyze in your program whether the destination vertex is mapped to a single thread or to a multiple to different threads. Okay, so let's see how a library writer would do this in this case. A simple way to do this in a compiler would be to a data flow analysis with a 3-point lattice, where you keep track of each index being either shared, independent, or constant. What I mean by shared is that index is mapped to multiple threads. Independent means that particular destination or that particular index is mapped to a single thread, and a constant is just a constant. And you can use like data flow analysis to figure out whether that destination, that write to new rank needs an atomic or not. But again, we do not want our library writers to understand data flow analysis. We want them to write it just as a library. So the way we do this in this case is the type vertex here, the type that denotes the destination vertex, is actually a struct in this case. Inside that, it has a vertex ID, which is a dynamic variable. So that will hold the actual vertex at runtime, or it will just produce the code for that vertex that it's currently dealing with. And then it has an enum inside it, which keeps track of whether this vertex is shared, independent, or constant across different threads. And that property of access is actually tracked as a static variable, which means it's evaluated in the first stage. Now what we do is all the operations that we do on this vertex type, this is happening on top of build it, by the way. This is not part of build it. This is the library that the user would write. What they do is when they overload all these operators, they actually update these properties to the lattice. So whenever you're doing sort of a plus on two vertices, like you're saying vertex A plus 1 or vertex, you should not be doing vertex A plus vertex B, but if you're doing sort of vertex plus a constant, what this does here is updates those properties. So if you're adding a constant to an independent variable, it still remains independent. So if you have an index mapped to different threads, like say index X is mapped to different threads, and you do X plus 1, that still remains independent. But if you do X plus like some other operation like X plus Y, where both of them might be independent, it becomes shared. Like you could have conflicts now because different values as they are summed up could now basically access the same index in the destination case. So basically the user writes sort of how to update these properties as part of the operations. And finally, when you use that vertex to access into an array, so in this case, whenever you do new rank of destination, at that time we check the property, and if it is independent, we generate a plus equals to. If it is not independent, we generate an atomic add. And the key point here is that if condition on the axis is a static variable, which means that condition will not be generated in the code. It will be evaluated in the first stage, and only one of these statements will be produced based on the context of your program. So like the way your program is written, it will sort of like keep on evaluating it and eventually produce one of the statements. And the basic idea is the user did not have to write any of like sort of compiler code to generate this. They just wrote it normally as a library would, and it generates different code for you. And this is another example of what I've said before. Like these conditions don't have to be at the top level. They could be like deep inside your loop, which is evaluated every sort of iteration, and you do not want it to like affect your performance. So yeah, generates efficient code based on the context of the invocation. I can get into more details of this, but I think we are running a little bit short on time, so I'm gonna go through this a little bit fast. But if you have any questions, I'm happy to answer this. Yeah. So other than this, our system has support for generating CPU and GPU parallel code. So we basically have simple statements like these builder annotate, which lets you annotate your generated statements like loops and conditions and even declarations with basically arbitrary pragmas that you want to add. And that lets you sort of produce OpenMP loops or any other sort of like pragmas you want to generate. We also have built-in passes in Buildit that take these special annotations like CUDA kernel and map multiple level nested loops to basically a CUDA code. So if you ever write a for loop with like 2 level nestings and put a builder annotate CUDA kernel on top of it, Buildit will basically automatically convert the body of that nested loop into a CUDA kernel and insert the call to that kernel in your generated code. So here n and m, by the way, are first stage variables, so the sizes are known, and the CUDA kernel is launched with the appropriate sizes, and the body of the loop is basically mapped to a kernel. Buildit also takes care of moving the data between GPU and CPU around the code, so that way you don't have to worry about it. You basically write your library as you normally would. So with all these sort of techniques that we have developed, we actually re-implemented the Graphite compiler that you had seen before was around 100,000 lines of code. We actually implemented the GPU part of the compiler, which is around like 50,000 lines of code, in just 2,000 lines of code. So the whole compiler, starting from the abstraction, the optimizations, code generation for GPU, everything inside 2,000 lines of code. And the key point is the performance of this generated code actually matches the performance, or in some cases slightly better than the original Graphite compiler. So what I've shown here is the execution time normalized to Graphite. So 1 here would mean that it's exactly the same performance as the original compiler. Anything less than 1 would mean that it's faster than the original Graphite compiler, and more than 1 would mean it's slower. So across 5 different applications, PageRank, breadth first search, connected components, shortest path, and between a centrality, and 9 different graph sets, we're able to get almost the same performance as the original compiler. But the whole idea is that we're able to do this in a fraction of lines of code, just 5% of the original lines of code. This was our previous work. Any questions about this before I go on?
Yeah, I have a question. So let's say in the case of matrix multiplication, for an example, how do you express tiling like transformations using Buildit?
That's a great question. So the way, let's run a simple example of a loop. I guess I don't have a loop example here, but okay. Suppose you want to implement tiling, right? First of all, what is tiling, right? Like you have a bunch of loop nests and you want to split some loop nests and you want to reorder those loop nests. That's the way a compiler engineer would think about tiling. But for a library engineer, what does a library writer, what does tiling mean here? It's just changing the order of iterations. So imagine they express those loops as just a bunch of like for loops for that particular application. So suppose they're writing matrix multiplication as an application, and they basically wrote like a 3-level nested loop to do the matrix multiplication. One way to do tiling in this case would be to just change the loop nest to have 4 loops instead of 3 loops, tile the innermost, or 5 loops instead of just 3 loops to tile the innermost 2-level loops. If you want to not always tile it, you want to tile only based on a specific sort of situation, then you would have an if condition there based on a first stage variable, where you would have either a 2-level nested loop or a 1-level nested loop. And they will have a tiled or not tiled implementation. So and because the condition is evaluated in the first stage, you would get one of the cases. You can take this idea and make it more like very general, where you could basically each of your loop nest is level of your loop is actually a recursive function call, and that each of the recursive function call has a if condition inside it, where it chooses whether to like break apart the loop into 2 loops or a single loop and generate the code. So again, this is not like you're manually taking a loop, splitting it, reordering it. You're basically writing your loops itself as a potentially tiled loop, basically, and then you use the indices from there to do the computation. I don't know if that does that answer your question?
Right. And how would you transform that to a GPU code? Now, in that case, you'll now have to write a kernel, and then you have to map that nested tiling into a kernel, right?
Right. So yeah, so that we can, like, the basic infrastructure support that Buildit provides is to, like, you can annotate any level of nested loop. They don't have to like appear in the source code at the same location. They can be like across recursive calls. And as long as you put the annotation, again, this annotation can be conditional, like this function, builder annotator is basically a function call. So you can put that function call inside an if condition and say, okay, if I want to map to GPU, put this annotation here, which will apply to the next 2 for loops that are generated, and they will be mapped to the GPU. So we can actually we actually have this implemented. We have a small sort of Einsam language DSL on our website. There's an online tool where you can just play with it. And that shows an example of how you can generate GPU, CPU, or not parallel, like serial code out of the same implementation just by putting conditions here and there. So you can basically conditionally put this CUDA kernel call based on any 2 loops, and the system will automatically convert those into GPU kernels. What needs to be sort of decided is whether that transformation is valid or not. Like you could have dependencies on those loops, and you do not want to map arbitrary loops to GPUs. You're parallelizing stuff that's wrong. That we leave up to the user. Like again, the domain experts know what can be done in parallel, what cannot be done in parallel. So we trust them to put the CUDA kernel annotation only where it makes sense. And that makes sense. Yeah.
Okay. How do you decide how much shared memory to use? Now.
Oh.
Yeah.
Yes, that's a very low level sort of like detail that the system doesn't care about. We basically, for shared memory, we just allow like the user to allocate shared memory. So again, when we have array declarations, you can annotate them to be shared, and the system will put them on the like as shared memory inside the kernel instead of like having it as a global memory. This is a very low level interface right now. Like this is basically infrastructure support to generate GPU code. We can build libraries on top of it. So for what we have done for the Graphite DSL example is we actually built a load balancing library. So we noticed that a lot of computations have this similar pattern where you have a bunch of edges to process which are sparse. So you need to sort of load balance them so that all your GPU threads are constantly utilized. So we actually built a load balancing library on top of it, on top of build it, and then you specify the body of the kernel by just calling this load balancing library. And that load balancing library internally has shared memory for doing sort of internal load balancing, for doing computations and so on. So again, the end user, like the one who is actually using this load balance library, doesn't have to deal with shared or like warp communication or whatever, but they can just sort of like use a very abstract interface. But the low level system that we have in Builded doesn't sort of decide that for you. You decide that. Like someone has to make that decision, not the system.
Okay, thank you.
Yep. I guess the high level theme is build it as a low level tool. It's not really it doesn't make decisions for you. You have to make those decisions. Okay, so let's continue ahead a little bit. I actually want to talk about this fun work in progress system that we are building, which is basically a high performance network DSL that we actually are currently working on, and we have some results out of it, but it's not published yet. So the idea that I started a year ago now was to basically create a modular configurable network stack. What I mean by this is, if you look at sort of network protocols today, there's essentially 2 extremes. You have UDP, which is simple and fast. It is stateless, and it doesn't have any sort of these fancy features like reliability or in-order delivery or congestion control, no handshake, nothing like that. It's a bare bones protocol that just gives you fast and simple communication. On the other extreme, we have TCP, which has stateful communication. It is reliable, in-order delivery, takes care of congestion control, has a lot of overhead though because of all these features. What if I wanted something in the middle? Like I want reliable delivery, but I don't want to pay the cost of congestion control. I do want in-order delivery, but I'm okay with like say some of the packets being dropped as long as the ones that are delivered arrive in an in-order way. There's currently no solution for this. Like, I mean, the solution is you have to make your own protocol, right? Like you have to build your own protocol and then you can deploy it. So what if we take this compiler approach to combine basically these different features that are available in TCP and let the user pick and choose what they want to produce their own stack? So what we have built so far is basically this system called NetBlocks, which is essentially like I like to describe it using this Lego analogy. So where we have a core, and each of these features that we have, like reliability, congestion control, routing, checksumming, or even like features that don't exist currently, like encryption, are basically these blocks that you can put on top of these Lego boards, configure them in different ways. So you can say, okay, I want this flavor of routing, I want this flavor of in-order delivery, and so on, and then combine that to give you a single protocol. Obviously, this would come at a cost, because when you sort of combine these features in a modular way, there's a cost to that abstraction, right? Like you have virtual dispatches here and there, or you have like conditions being checked everywhere around to check, like, do you want this flavor of reliability? Do you want that flavor of reliability? Or what level of encryption you want, whether condition is enabled or disabled, all those kind of things. But again, because we implement this and build it, we can sort of like partially evaluate all those overheads. So the modularity overhead of like combining these simple features, the condition overhead for like choosing which flavor you want, all that can be evaluated in the first stage, and you get very specialized code that's sort of tailored for your network sort of application. But one thing that we sort of, okay, this is an overview of how the system works. We basically have this core which implements a bunch of paths, where these paths abstractly refer to the control flow that's taken at runtime. So like you have a send path that's invoked when a packet is being sent, or an ingress path that's executed when a new packet comes in, established de-establishes for like connection management. Now, what all of our features are implemented are these modules M1, M2, M3, M4 that can basically install hooks into these paths by like basically implementing a virtual function, and they can implement how the behavior of that path changes when that sort of module is invoked. But this hooking and this virtual dispatch is all in the first stage. We evaluate through it, and we basically produce straight line code for each of these paths that is basically optimized for that networking stack. That's the like a 10,000 feet view of what's happening inside the system. But one key thing that is missing from this methodology is how do you actually change the layout of the packets? So when you actually create a new custom protocols, you have custom headers, and you wanna like not waste too much space in your packet headers to have like all the headers that you don't need. Like for example, you don't need a sequence number if you don't have reliability or in-order delivery, or you don't need sort of IP addresses if you're not doing routing. You can basically do it based on just MAC addresses. So how do you actually change the layout of these packets using a system like this? Build it lets you like specialize code, but how do you specialize data layouts? And that's the problem that we tackled to this paper. And normally what you would do in this case is you would basically define a struct that has all your fields as members in them, and then you would sort of use that struct as for manipulating the data. So you would cast the buffer, the packet buffer, into a struct, like a pointer to the struct, and then you update the fields of that or read the fields of that to update those fields. But you cannot do this in a sort of metaprogramming way, because how do you change the struct itself when you have to disable enable fields? Like you cannot say if checksumming have a checksum field. Like how do you do that? So what we did is we basically realized that the problem of describing layouts is actually describing how to access those fields. So we first converted the problem of having layouts into code. There's a lot of details here that I don't think I want to get into right now, but the high level idea is we for each sort of layout that we have in a packet, we express how to read and write those fields as these very simple virtual functions. So we have get integer, we have set integer, get offset, and so on, which basically implement the logic of how to access a particular field. So in this case, I have a generic integer member, like integer member. It has two properties, size and alignment. And based on those two static properties that are known at compile time as in like the first stage, we basically compute the size of the field and the offset of the field. So offset is where in the packet that a particular field lies. And then we basically have a get integer function which does the address computation and returns the value for that field. And then the modules that actually implement the logic can access these fields using this net packet or this dynamic object that they can basically call this get integer or set integer function. But because this is all written on top of build it, none of these sort of strings or the array, like the indirection operation, appear in your generated code. Your generated code basically just has the exact sort of address computation followed by the dereference to get you the value and set the value. And now what you can do is you can actually conditionally choose which fields to have in your code versus not have in your code. So you could say if I have checksumming, then add the member checksumming, and that will change the entire layout because all the fields basically talk to each other to see what order they are in and what offsets they're computing and so on. What we basically did is we converted the problem of layouts into code, and we already know how to specialize code. Taking this a little bit further, you can actually then implement alignment, where you can say if a particular field is aligned, here's how you change the offset computation. You can also basically do bit masking. So you can say, okay, if the sizes are smaller than a particular field. So basically the high-level idea is you can say, okay, your length is a 2-byte field, but I know my packets are always going to be in the range of, like, say 0 to 64 bytes. I don't need a full 2-byte length. So what the system can do for you is automatically shrink the number of bits required to represent those sizes into fewer bits and generate specialized code to do bit masking, offset computation, and sort of like shifts to give you the exact value. So that's sort of under this abstraction of get integer and set integer. The user still sort of just says net packet of length set integer, and it automatically generates code to do the shifts and the masking for you. So there's a lot of details here that I'm not getting into, but eventually this paper will be out and you should be able to read about it. What we get out of this is we can take a protocol like this, which has this is basically UDP on top of IP on top of Ethernet, and there's finally some payload, which has basically a lot of useless fields. So, for example, if you're targeting a specific application, like in a data center, you're doing some distributed training, you don't need a lot of these fields, right? Like you don't need versioning, you don't need time to live, or some flags or fragment offsets and so on. Those are useless fields. Whereas there are some of the fields that are like redundant. So the ones in yellow that I have shown here are basically not serving an extra purpose. So there's checksumming in the UDP, there's checksumming in the IP. There's source and destination IP address. There's also destination source MAC addresses. If your system is all like in a all-to-all network, you don't really need routing. So those are redundant fields. There's also length in the IP header. There's length in the UDP header. So first thing that we did with this optimization is we actually got rid of all the useless and like redundant fields, and that brought down our sort of packet size to I think 32 bytes in this case. And then finally, we shrunk those fields. So we say, OK, if your system doesn't need 48 bits for source and destination, can we shrink them down to 4 bits? Because we only say have 16 nodes on the compute. And if we can shrink down the length to just 1 byte and the payload, then we can basically bring down the header to just 2 bytes of header for the payload. And this is all happening in a very modular way. So the user doesn't have to change the implementation of the modules. They just like sort of change some parameters, and it generates vastly different code for the network protocol. I don't currently have the network, the results for this, but basically we can optimize packet layers. We can customize how those headers are generated and offer the end user, basically the user of these protocols, a trade-off in terms of performance and what features they have. So the idea here is pay only for what you need, kind of a thing. Yeah. Any questions about this? Sorry, I breezed through this a little bit just because we are maybe running short on time, but if there are any questions, I'm happy to answer. All right, I'll just talk quickly about another thing that we sort of that makes Build It more usable, which is another system called Detox, which is basically a debugger extension. So what we realized is DSL writers for them, we have simplified how to write compilers and how to generate code. But how do you debug that new language that you have made? Like if you're writing programs in this new language, how do you debug this? So we built the system called Detox, which is basically an extensible and contextual debugger for DSLs. What this is basically it's a library again. Instead of taking a compiler approach or like an extension approach, we basically build this library that you can include in your code and include arbitrary information in your generated code that you want to show inside the debugger. So we basically have a bunch of API functions that you can call to insert information about the original source code, about the original sort of DSL variables that can now be accessed inside the debugger. So we basically added these commands xpt, xlist, xframe, xbreak, and xdelete, and xvars, which let you look at the extended state of the program. So in the case of like say the DSL like Graphit, we can now look at the original vertex sets, and we can look at where the original execution. I think I have an example. Yeah, so here I have an example. So these commands let you see the DSL state of what you have encoded. And then what we did is we applied our system, this Detox, to build it itself. So what this does is when you run program in multiple stages and you attach a debugger to your generated code, we can actually show you what the original program was. So we can show you the first stage execution in your debugger, and that way you can sort of like debug through the stages. What this means for DSLs written with our system is you basically get debugging support for your language without having to write a single extra line of code. So if you write your DSL with build it at this point and you enable Detox in a compile time flag, then you actually get a view inside your debugger like this. This is unmodified GDB running, by the way. There is not a single line of code changed to GDB. You can basically run this commands like xvars, which show you in this case like a matrix multiplication DSL. It shows you the original line of code. It shows you the internal variables like whether it's a constant value, whether it's not. So like all the stuff that is there inside the compiler gets shown as debug time information, which makes it easier to debug all this code that we generate. I'm gonna quickly just go over this. I think I can skip this for now. But I quickly want to talk about what's happening with Build It these days. Where are we in the process? Obviously, we have built a lot of DSLs, but we are also expanding in different directions. So the first thing we are doing is we are actually expanding upwards, where we're building a lot of application DSLs on top of Build It. So Breeze is one of the DSLs that a master student who's working with me has implemented. It's a regular expression DSL that generates different implementations for your regular expression. So you basically provide a regular expression and it generates code to match that regular expression, a high performance code to match that regular expression. We also have recently, one of the PhD students who graduated from a group built this compression DSL for images and videos on top of Build It. So she wrote her whole implementation as a library on top of Build It, and it generates high performance code to compression. And I'm myself working on NetBlocks to implement network libraries. This is sort of like the upward expansion of Build It. We are also doing a downward expansion, like by targeting different architectures. So currently we already support CPUs and GPUs. There's more infrastructure support being added for GPUs, but CPUs and GPUs is what we currently support. We have a PhD student who's working on extending Build It to work with FPGAs. So instead of writing it as a backend for Build It, they're actually implementing it as like a system inside Build It that has a specialized array language that you can generate code for FPGAs. The benefit of sort of like using the system, using our system, is all these sort of applications can now choose to target different backends without having to write like a lot of code again and again. So this upward expansion towards application, downward expansion towards architectures. And we are also doing sort of a sideward expansion where we are adding toolchain support around Build It. So Detox that I just talked about, the debugger is one of the examples of what we are doing. I'm also recently starting this project called TBD, or Dynamic by Default, which basically lets you take any normal C++ code that's not written with Build It types and automatically convert it into Build It code. So that's like a Clang plugin that lets you basically make. So currently any C++ code that you have, it's static by default. So everything is running in one stage. DBD can basically take it and split it into multiple stages automatically for you. So that's like a toolchain support to build it more usable. And I like to describe this as like a quasar. The heavenly bodies that we have, and because it looks like there's a upward expansion, downward expansion, and a sideward expansion. Information about all these projects are available on our website, builder.so. And most importantly, we are looking for contributions. So if you are interested in like contributing to any of these applications, just visit the repository, create an issue, and we are happy to like accept contributions for these projects. Yeah, I'll take any questions that you have at this point, and then I just have a final closing slide.
So I have a question. Regarding FPGAs, so from what I understand is that you're using C++ as a language to as a platform to build all these DSLs, right? So how do you code generate for FPGAs? Because I think there might be C++ languages targeting the FPGAs, but I don't think there's a default C++ language would do it, right?
That's right. So there are currently multiple ways to generate code for FPGAs. We are taking the HLS approach. So we are generating C++ code out of BuildIt to map it to FPGAs. But it's a significantly, the gap here is we want the user to be able to write higher level sort of code instead of writing like very low level FPGA code. They are basically writing these loops and they're writing like array operations. They are saying like, here's an array, do a plus on this array. Here's an array, multiply with this with another array, like a very high level operation, and we can generate like very low level optimized FPGA code for it. That's the approach we are taking. But it's again C++ to C++, because of just the way of like the nature of how BuildIt is built. It's like a source to source, like it's a multi-stage compiler approach, right? Like it takes C++ code, produces C or C++ code. So we're using like the HLS in the backend to generate FPGA code. Now, HLS doesn't always work for most applications if you're writing it by hand, right? Like it's very hard to write like optimized HLS for FPGAs. But because we are taking this compiler approach, our hope is that we can generate like really complex optimized code when the user writes very simple code. The way sort of the system is built right now, it's not a very generic system. Like you can't take arbitrary built-in code and then just compile it onto FPGAs. It has to be written in a very specific way, like using that array abstraction basically. But our hope is we can do applications like graph computations or tensor operations with that and target FPGAs. Yeah. This is also a work in progress right now. We have a visiting PhD student who is working on this project. So it's not complete, but we have some initial promising results.
So yeah, I have a question. So BuildIt is a C++ library, right? So do you notice any like performance or other kind of differences based on the C++ compiler you use with BuildIt, like GCC versus Clang or some vendor-based compiler, or is it largely like compiler agnostic?
So here's the thing about BuildIt. It's like there's the first stage and the second stage, right? The first stage, we don't really care about the performance so much. Like it's okay even if that runs slow because you're running it once and then you're running it multiple times. The key thing about BuildIt is no matter what optimization level it's compiled with, like you can compile it with O0 and it'll produce the exact same code because it's the logic there is to produce the operation. So that doesn't really matter. Obviously, the generated code depends on the architecture. Like if you're trying to vectorize the code, some compilers are better than the others. I mostly like test all the implementation with Clang or GCC, just because we're mostly targeting x86 right now. We haven't done any vendor like specific architectures. And for GPUs, it's mostly CUDA for us. We haven't tested it with OpenCL, but yeah, I don't think I've noticed too much a difference in the low-level performance, mainly because I think we work in this like DSL space, right, where the higher-level optimizations matter more than low-level optimizations. Like, yeah, you might get a few percent, like 5 to 10% difference based on what the backend compiler does, but we don't really care about that so much. We're looking at very high-level optimizations, which like sometimes give 2x, 3x performance speed up. That's because like we are just changing the algorithm, like we're changing how to compute the operation. So our focus is more at like this big optimization rather than like the low-level optimizations.
Thank you.
But I guess you can always see a lot of difference in CUDA. Like if you do a very small change in what code you're generating, the GPU performance it changes a lot. And that's also sometimes a little bit dependent on the compiler. Like if you move between CUDA SDK versions, same code sometimes runs faster and slower. So that we have to deal with a little bit.
Yeah, there are cliff effects in generating GPU code, and if you change the parameter a little bit, and you drop down the cliff.
Yeah, you add like some very innocuous looking statement somewhere, it increases the register pressure, the whole block size just drops, and your performance is 2x 3x slower. And it's very hard to guess that, but that's like the standard GPU struggle. That's nothing to do with like code generation. It just becomes harder to notice in code generation because the user writes something else and the generated code is very different based on like one small change, and your performance is very, very different. Yeah.
Right. Yeah, exactly.
Any final questions from the audience? Otherwise, we're on top of the hour. I think there's a question in the chat.
Yeah, so just to follow up on the thread, is there any plans for something like hardware cost model optimization?
So I'm not working on that myself. We do have folks in a group working on like cost models and using those cost models learned or like actual into the compiler to optimize stuff. Build it again is sort of like I think of it as orthogonal to optimizations. It's more of a tool to generate code and transform code than making decisions. I like to personally like leave the decisions to the user. So I don't think in the near future we have any plans for extending build it for cost models. But there's definitely like other research in our group that's focusing on like automatic optimizations. Yeah, it's such a cost models are hard, and making decisions is difficult. So I focus myself on building nicer, like fun, good looking abstractions. That's where my interest lies.
But your group also works on the machine learning side, right? Building building cost models using deep learning, machine learning techniques.
Yeah, there's folks in a group that work on building cost models by learning or by actually measurement or whatever. And then we also have work in a group that optimizes code based on those cost models. We, in fact, actually, let me just quickly plug that in. For the Breeze project, we are currently working. So the Breeze is the regular expression DSL. That also follows the same model of algorithm and schedule. So you specify the algorithm, which is the regular expression in this case, and you separately specify sort of like decisions on how to compile that. So for example, like a quick example, if you have a branch in a regular expression, you can map it in different ways. You can either do like a backtracking, or you can simultaneously match all the branches together, and that has performance implications. So we ask the user to tell us how to compile that. We are actually currently building a machine learning framework to automatically guess that schedule based on the regular expression itself. So we are aiming for an end-to-end system where the user just gives us a regular expression and we generate the most optimized code for it. That's sort of like that's the goal. So I'm trying to use it, but it's not part of build it. It's on top of build it in a way. But yeah, there's other research in a group that's using machine learning for cost models, for optimizations. Yeah.
Okay, yeah, thanks for sharing. Yeah, that's really interesting.
Okay, I'll just go to my last slide, just plugging in my socials. So I actually, I'm a 6th year PhD student. That's my website. If you want to reach out to me, my email is there. So you can, if you want to like talk about research or any of these projects that I'm working on, please feel free to hit me up. I actually also do a system stream every Saturday where I talk about Build It and I talk about like low-level systems programming. That's my Twitch channel, and I also post the same videos on YouTube. And that's my Twitter handle if you just want to hear me rant about programming languages and research in general. Yeah, thanks a lot for having me. This was really fun.
Nice.
Yeah, thanks a lot for this. And, we planned it rather quickly. Also, thanks to Vedant for connecting me to you. And it's very, very interesting. And I didn't really know that much about DSLs. I'd heard a little bit about Halide during a talk from Qualcomm and how Qualcomm uses Halide in their smartphone cameras. But yeah, it's quite amazing. So thanks a lot for the talk. And we'll definitely be reaching out to you with the recording and stuff.
Yeah,
just-
thanks a lot for having me. Yeah.
Yeah, just want
Sorry,
to
go
make
ahead.
one point. Yeah, I think this is I've seen a similar kind of model where if you've noticed Mojo programming language, they do a similar approach where they move all the optimizations like vectorization to a library and then let the domain experts write that. And so your concept is remove the compiler expert from the loop and let the library writer write all of the optimizations and what they want, and then incorporate that into the library and not have the compiler expert in the loop, right? Yeah, I think Mojo is also doing a similar kind of approach, and yeah, it's really good to know that there's a converging path here. Right.
I mean, that's actually, it's a need of a time, right? Like there's so many languages popping up everywhere. You cannot expect like compiler engineers to be in the loop all the time. And it's not just like developing those languages, right? There's also like extending, fixing things, and how much the way these domains are evolving, like machine learning or any of like high performance domains, you need some way for them to like automatically prototype these languages and start writing programs with it without having to wait for like compiler engineers. And I mean, it just makes sense to like, yeah, Mojo also it's a need of the time more than like a nice thing to have.
Yeah, totally. Yeah.
Like I haven't actually got a chance to play with it myself. I would probably in some near future, but yeah, I think we took a very different approach. Our goal was to keep it as familiar to the end user as possible. So like, because these folks already write these libraries in C++, we were hoping that you can just take their code, change some types, and make it work with our system. I mean, we can definitely do, you can do a lot of like cool things if you take a compiler approach, like you write a new language and which lets you just like have either multi-stage programming or just like compiler-ish code as like built-in features in the language. We wanted to avoid that so that like the users have familiarity with the system. But yeah, I mean, both directions you can get some pros and cons out of them.
Right, I think library approach is more easy to get started with and more scalable. Instead of learning a new language, writing a new library, and shipping it with in your production stack. Right? And Mojo is in its infancy, and it's really hard to know what sort of compiler bugs. It's a software, so you also have bugs, and yeah, I think library approach is much more safer. And you're also building on top of C++, which is much more a stable and a mature language.
Yeah, I mean, obviously our system also has bugs in it, which we try to iron out from time to time. But yeah, like, I mean, fixing bugs in libraries are much easier than fixing bugs in compilers. I mean, okay, to be fair, Build It itself, like if you look at the internals of the library, it looks more like a compiler. Like inside we have these ASC analysis, transformations, and everything, like all the usual stuff from compilers. But we try to keep that away from the user as much as possible. So I mean, when there are bugs in the compiler, I have to fix those, not the end user. Yeah.
Right. So one thing I forgot to ask in the first place was that do you also parse C++ code? So do you actually write a parser for that and then do all these tracing and control flow analysis, that sort?
Not really. We don't have a parser or anything. We actually, our whole code compiles with unmodified C++ compilers. You can basically throw Clang++ at it and G++ at it and it run, because we don't, like I said, we don't actually parse any of the code. We just overload all the operators and we look at the program through this window of the operators. So like whenever the operator plus is invoked, build-it's code gets invoked, which basically tells it, okay, there must have been a plus in the original code. It doesn't actually see the code, the loops. I mean, if we had access to the source code, we could directly just get for loops out of it. We didn't have to go through this this way of like extracting, tracing and extracting. You could just see the program and evaluate it. But we didn't want to take that approach. We wanted to keep it through a pure library approach. So we don't actually parse any of the code.
Okay.
And there's actually good reasons to not do that, because if you parse the code, then you have to sort of manually decide which part of it gets evaluated versus which doesn't get evaluated, and then you run into like specialization becomes very hard. Like if you parse and you do transformations on the extracted code, making it specialized is very tricky, because you can have like static and dynamic interleaved as part of expressions, as part of statements, like nested if conditions and so on, and it becomes tricky to handle it. But because we just like explore these different traces, the G++ compiler does all the work for us to decide which part is executed in the first stage and which part is executed in the second stage. So that simplifies our work a lot. All we do is record a sequence of operations and then try to put them into a single consistent program view.
Okay. Yeah. I think I get it now. Yeah. Okay. Does anybody have any questions?
I just wanted. Hi, Ajay. I'm Aditya.
Hi.
I just wanted to thank you for taking so much time for presenting, and I see you on Twitter, so I just wanted to encourage everyone to just follow you, because they might get connected with you, and then they can get to follow like what you do there. And I mean, some of the things you post are humorous, but some of them can be enlightening to like folks who can get like right direction and get in touch with you. Yeah. Awesome.
Nice to meet you, Aditya. Yeah, no, this Twitter, the handle that I have on the screen right now, is my personal Twitter. So it's a mix of a lot of things, including ranting about research, talking about music, food I like, and a lot of things. So it's there's like a warning that comes with it before you follow this. There's another Twitter that's purely academic, which I use only for talking about research. You can choose to follow whichever one you want. But yeah, if you're following this one, just there's a lot of stuff on that Twitter. But it's fun. I talk about research a lot too, so it's not just fun stuff.